Another type of reaction is called a gas evolution reaction. These are reactions that evolve gases. So that means a gas is formed. Some reactions do this directly. If you mix sulfuric acid with lithium sulfide, you're going to get hydrogen sulfide gas and lithium sulfate aqueous as products. What you see when you do this, like in a test tube, is you see bubbling or fizzing as the gas comes out of the solution. This gas smells like rotten eggs, so you really don't want to do that in an open room. Other times, you get an intermediate product that's unstable and decomposes. So if we mix hydrochloric acid and sodium hydrogen carbonate, this is baking soda, what it does is it forms carbonic acid and sodium chloride. We're swapping partners here. The hydrogen and the sodium are switching places, and so we get carbonic acid and sodium chloride. But carbonic acid is unstable. How do we know that? Well, that's one of those things you just have to memorize. So this is unstable, and this decomposes into water and carbon dioxide. And then there's also the sodium chloride. So this generates a gas, but not directly. So there are 4 types of compounds that give off gases. And these are listed in table 7.4 in your textbook. So sulfides, like that first reaction we looked at, don't have an intermediate product. They just give off hydrogen sulfide gas. So here's an example of that. An acid plus some metal sulfide gets you H2S gas and an ionic compound. The other 3 types generate an intermediate product. Carbonates and bicarbonates, sulfites and bisulfites, ammonium, all generate intermediates. The intermediates are carbonic acid, sulfurous acid, or ammonium hydroxide. And these decompose into carbon dioxide, sulfur dioxide, or ammonia. So this, I think, looks all very random, doesn't it? Like, how are we supposed to remember that? Well, let's look at this. So this carbonic acid decomposes into CO2 plus H2O. So look at that formula. If I pull out the H2 and one of the O's, what do I have left? CO2. The same thing happens with this one. It's going to lose a water molecule. It's going to lose the 2 hydrogens and one of the oxygens, which leaves us with SO2. And this one, not as obvious, but it's also losing H2O. It's going to lose this H and this O and one of those H's. And what's left? NH3. So when we do these reactions, we predict the products in the same way that we've learned for the precipitation reactions and the acid-base reactions. We're going to take them apart into ions, switch the partners, and see what we get. The little twist here is if you get one of these things, there's 3 of them to remember. If you get one of these 3 things, you need to remember those guys are unstable. They will lose a water molecule and form a gas. So mixing ammonium chloride with potassium hydroxide. The potassium and the ammonium switch places, so you get KCl, and you get ammonium hydroxide. The ammonium hydroxide comes apart into ammonia and water. So let's do some examples. So here are steps. First, write the skeletal equation with the reactants and the products. And the products forming is what I just said. Take the reactants apart into ions, swap the partners, put them back together into compounds, and that's your skeleton of an equation. And then what you have to recognize is that if you get H2CO3, H2SO3, or NH4OH, that those are going to decompose into water and what's left of that formula. So you do that, and then you balance the overall equation. Let's do an example. Write the molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So first we need the formulas for these guys, right? Hydrobromic acid. This is an acid, right? It's got acid in its name. Is it an oxyacid or a binary acid? It's a binary acid, and this prefix hydro is what gives that away. Oxyacids do not start with hydro. Hydrobromic means it's just hydrogen and bromine. So we look on the periodic table for bromine, and we find out that bromine has what charge? -1. So I'm just going to write little notes to myself up here. Bromine has a -1 charge. How many hydrogen ions will I need to balance that charge? Just one, right? So I need H plus and Br. So that's my hydrobromic acid, HBr aqueous. And we're mixing that with aqueous potassium sulfite. So actually, I should have written my notes down here instead. Potassium. Potassium is K. What charge does potassium have as an ion? +1. How about sulfite? SO3, 2-. Sulfate is SO4, 2-, and this is the light version. It's got one less oxygen. Then we look at the charges on these, +1 and -2. We can do the crisscross thing, or we can think, well, we need 2 of these to balance the charge on that, and so we're going to get K2 SO3. That's not cool. SO3. To predict the products, swap the ions. So 2 couples coming to a party, mingling, and seeing what happens. So we're going to end up with K plus and Br minus together, and H plus and SO3 2- together. This one's +1, -1. We just put them together. KBr. And then to identify the state symbol, we would have to look at our table of solubility rules. Potassium compounds are always soluble. So this is aqueous. And this would form what? H2SO3. And that's an acid, right? So that would be aqueous. I didn't space that out well at all. You'd think I'd have that figured out by now. When you see this guy, little red flag or little bell should go ding, ding, ding. That's one of those 3 things that decomposes. So this is, H2SO3 is not stable, it falls apart. So this guy falls apart into water, which is a liquid. And then we can look at this and say, well, if we got rid of the H2 and we got rid of one of the O's, what do we have left? SO2. That is a gas. So now we could take these pieces and put them all together. HBr aqueous plus K2SO3 aqueous. I'm going to skip that, this guy in the middle. I've got this guy plus these guys up here. I'm going to get KBr plus H2O plus SO2. And then I need to balance this. Is it balanced by itself? Sometimes they are. It isn't, is it? There's hydrogens and oxygens all over the place. Don't start with those. Start with the metals. The metal K2. So we've got 2 potassiums here. There's only 1 over here. So let's fix that. Put a 2 here. And then that means there's 2 bromines. And over here there's only 1. So we'll put a 2 over there. Here's 1 sulfur and 1 sulfur. Now let's take care of the hydrogens and the oxygens. 2 hydrogens and 2 hydrogens. For oxygens, we've got 3 oxygens here, and 1 plus 2 is 3 there. So there's our balanced chemical equation. These gas evolving reactions are important, but I understand that not all of you can learn all of the material, right? And sometimes you just need to focus on the more important things. It's like cleaning the house, right? You can't dust the ceiling fans every week, right? If you get them once a year, sometimes you're feeling lucky. This is like a ceiling fan. Okay, this is something that you could ignore and still pass the class. The other equations, the precipitation, the acid-base neutralization, focus on those. If you've got those down, then by all means, get a handle on the gas evolution reactions. If you're struggling with the other ones, just ignore the gas ones. Somebody had a question. Yes?
So when you're partnering up with ions,
Mm-hmm.
you don't pay attention to the coefficients when you're doing the product, basically?
Right. When you're partnering these ions, the coefficients don't come into play. When you're putting this K plus and the Br minus together, you are only looking at the charges. Doesn't matter if there's coefficients in there, you just ignore those for the time being. You settle the coefficients at the end. Does that help? Any other questions? I love it when people ask questions.